Meet Madison. She's a great person because she wants to help people. That's why she's an Asurian expert. Asurian has many types of experts providing technical support to their customers. The experts come to people's homes, they work in stores, they give phone support, and they give messaging support. Madison works on the messaging support team by chatting and messaging with her customers. And she enjoys what she does, but she has a tough job doing it. That's because she has to retype a lot of messages again and again every single day. And it's really draining. This is not efficient for her. Or in corporate speech, this is a pain point. Here's an example of a message she has to type very often. Wouldn't you also get tired of typing this message every day, again and again? And here are other messages that she keeps on having to retype. Now, this is not just Madison. In truth, we're dealing with the problem of a much larger scale. You see, we have hundreds of experts, just like Madison, who need to respond to tens of thousands of sessions every single day. Hi, I'm Matityahu Sarafzadeh, and come and see how we used AI to make Madison's life easier. I'm going to share with you our journey with the stumbling blocks met upon the way, while building for Madison a system to help her avoid retyping the same messages. We'll talk about the challenges faced during the data collection process and the challenges faced during the modeling process. But finally, we'll see the solution, which helped us reach our goal, reaching a high accuracy model with the little amount of data that we had available. But first, a little bit about myself. I was born and raised in Houston, Texas. Yes, I also got hit by a car. Moved to Israel in 2010. I've been working in AI since 2015. A year later, I earned my bachelor's degree in telecommunications, systems engineering from Jerusalem College of Technology. I've been working as a data scientist by Saluto by Asurian since 2019. And in 2021, I became the data scientist team lead. My job at Saluto is to make Madison's life easier. So one of the gifts that our team gave her was the Can Messages feature, a list that was prepared of frequently used messages where Madison can simply scroll through, select, and send to the customer that she's supporting that message, thereby saving her much time from retyping that same frequent message. But we still had a problem, because now Madison's Can message library grew very large. In addition to the default list that we gave her, she has her own customized list of her own personalized Can messages. So now it takes Madison even longer for her to search for the desired message. So we decided to use AI to automate and auto-suggest the Can messages, saving for Madison much time instead of going through that very long library looking for that one message she wants to send. And for the first iteration, the focus was on predicting the permission to troubleshoot Can message. Why was this message selected? It was a business and a product decision. It gives assurance to the customer that his problem will be properly investigated, and it also creates a unified language amongst the experts. Here are some examples of the message. Can I ask you some troubleshooting questions? Or I need to ask you a few questions to understand your issue. Will that be okay? The data collection, creating something from nothing. You see, ideally, the way I would like to collect data is very simple. Ideally, go through all the sessions that happen. Some which use the permission to troubleshoot Can message, and some which didn't. Collect it all together, run a model, and that's it. Everyone lives happily ever after. However, we found very few sessions that actually used the default permission to troubleshoot Can message, because many sessions weren't troubleshooting related. And those which were, not necessarily did the expert send the Can message. And even when the expert did send the Can message, many times they used their own personalized version of the message. So we needed data. And we introduced some NLP fuzziness to help us label more data for the model. Fuzziness is the technique of finding strings that match a pattern approximately rather than exactly. Take the word apple inserting misspellings of it. Fuzzy matching would join them all together, would cluster them all together. And we devised the fuzzy match hybrid algorithm, consisting of regular expressions, perfect match, the edit distance, and manual handpicking. The edit distance, by the way, is a method which measures the amount of changes needed to get from one string to the next. So with this combined algorithm, we were able to find more messages, because now we're finding messages that match a pattern approximately rather than exactly. However, this still did not yield enough data to train a model. So we moved to the power of semi-supervised learning. Semi-supervised learning is a method where we combine a small amount of data with a large amount of unlabeled data, a small amount of labeled data, and a large amount of unlabeled data during the training stage, thus helping us deal with our problem of a small amount of labeled data. In addition, research has indicated that a semi-supervised learning problem can give considerable results with less the amount of data compared to a fully supervised learning project. And this was our semi-supervised algorithm. We had a cold start, that few list of CAN messages, that very small list. So we started with that pool, those permission to troubleshoot CAN messages. Then we calculated the fuzzy match with all the other potential CAN messages, all the other messages that happened in sessions. And if it matches our threshold, we added it to the pool. Then, at least when it was scalable, reviewed, verified, and removed anything incorrect, cleaning that data. And then finally, rinse and repeat, going back and doing it again, thereby growing our pool in each and every run. And it got more interesting as it evolved. At first, due to the limited amount of data we had available, that cold start, we had to start with the weaker base model, our fuzzy match hybrid algorithm, where the output of that model was used as the label for the given sample. However, once we were able to obtain enough data, we became a Charmander. Charmander. No? I forgot. Charmeleon, thank you. You're paying attention. And we're using ML-based models, such as Bag of Words, TF-IDF, and LSI. Once we got even more data, this one I won't forget, that's a Charizard. I got that on my first deck. We're able to use deeper learning models, such as transformers, LSTMs, and encoders. But again, these are only soft labels. Labels that are generated by the output of an algorithm. In semi-supervised learning, we also need gold labels. Gold labels are those high quality, gold, human labeled data. But we don't have any. That's exactly how we got into this problem in the first place. So we created a session tagger program to generate synthetic data by manually injecting our target CAN message into sessions which didn't have the message but could have benefited from it if it did. And the results? For the synthetic data generation, we collected a few hundred labels. Those are those gold labels, those high quality human labeled data. And from the fuzzy algorithm, we collected about 1,000 labels. These are labels which are set based off the output of an algorithm, the soft labels. And with this, we move on to our modeling process, urging that nothing to learn something. A little bit about our model's features. We use the speaker as a feature, the customer, the expert. We also use the message number in the session. What number that message was in place of all the other messages in the session. The 4th message, the 8th message. We also encoded the message text with Google's universal sentence encoder. And we use the length of the message as another feature. Now, these features were processed on that message and the 10 previous messages leading up to that message. In other words, we had a 3D data set of n samples and all the features, and then another dimension of another 10 messages leading up to that message. So, time series data, right? We took the session and we split it into blocking windows of segments of 10 messages per each. And we didn't have overlap, it was blocking. The label of that sample is the next message of permission to troubleshoot CAN message that we generated right before. And this left us with a huge imbalance, as our message was used, at most, only once per session, out of the many messages a session could have. leaving us with a class ratio of the label of a 98 to 2%. And as you probably predicted, the model could not converge. So we have to re-engineer our data set by undersampling, moving from a target label ratio of 98 to 2 to 89-11%. The objective was to increase the ones presence in the data set and help the model better learn from them. And the model began to converge. This was due to the proper label proportion. In other words, the imbalance was high enough to resemble the reality, but low enough for the model to converge. So now we're heading in the right direction, but we're not optimized according to the business problem yet. You see, the model's loss function did not take into account their label imbalance. The loss was learning mostly from that zeros class, that 89% representation in the data set. But that ones class is also important to learn from. I would argue even more important. But we just did not have enough of them in the data set. As a result, we introduced the binary focal loss to help the model better learn from that lesser counted label. Also, on a product level, we used the F1/2 score instead of the MCC as a validation metric because precision was slightly more important than recall. At a product level, we prefer the customer's experience, the precision, rather than the conversion of the session, the recall. And this was to hold the retention and the happiness of our users. Now, what's a focal loss? Imagine you're at a soccer game. Barcelona versus Madrid. With your 100,000 fans in the stadium. All of a sudden, there goes Barcelona. Scores a goal. Goal! 70,000 fans, Barcelona's cheering in the air. Now, at home, everybody's able to hear those 3 TV reporters. But how? They're in a stadium of 70,000 fans. How can they hear them? Because there's a loss. There's a focal loss. The sound room amplified the noise of those 3 TV reporters and decreased the noise generated by the 70,000 fans. And the same here. The focal loss amplifies the weights learned by the ones class and reduces the weights learned by the zero class, letting the model better learn from that smaller class in the data set. And the rest was history. The loss converged, the F1/2 increased, and with early stopping before the overfitting and optimizing our threshold from the PR curve, we received the final results of the model with F1/2 micro of 85% and F1/2 macro of 64%. Even more interesting, further analyzing the model's results, we learned that many of the false positives were acceptable if they happened in real life. This was due to the high variance amongst the experts in their message sending habits. Sometimes an expert would take a very long message and split it up into multiple messages, even using a question mark as his own message. So, when our model predicted the can message a little bit earlier, it still would have been acceptable if it happened in real life. Our next steps would be using a scoring method to credit those false positives which are still acceptable. In addition, we like to try other models, GPT-3, BERT flavors, other encoders, to help us reach a higher accuracy. And last, our goal is to predict more types of can messages, in addition to the permission to troubleshoot can message. So now, next time Madison is on a messaging session, and she should use the permission to troubleshoot can message, the model will suggest the message to Madison, making Madison's job, bringing people closer to the technical devices, much easier. If you're looking, just like all the cool people, team is looking to hire. Our main goal in our pitch, I would say, is answering those big problems with a small amount of labeled data. So shoot me your CV.